Welcome to State of Simulation, the podcast all about multiphysics simulation where we stay up to date with what's working, what's not, and what needs to change. Each episode features an open conversation with the engineers and technical leaders shaping the future of physical product development. I'm your host, Jukka Knutinen, and in today's episode we're speaking with the chief scientist and co-founder of Quanscient, industry professor Valtteri Lahtinen. Valtteri leads quantum algorithms research at Quanscient Quantum Labs, one of, if not the most accomplished teams in the field of quantum algorithms for CFD applications. In this conversation, we talk about exactly that, quantum computing in physics, specifically CFD simulation. We discuss what has been achieved so far, what is possible for industry customers right now, what's next, and what the intermediate steps toward full-blown quantum advantage look like in practice. This 25-minute conversation contains everything you need to know about the current state of quantum computing in physics simulation today. Without further ado, let's get started. So, what exactly is the Quanscient Quantum Labs doing?
Right. So as probably many of our listeners know, Quanscient is a physics simulations company, and we're doing that for, in particular, like engineering R&D type of multiphysics simulations. And what Quanscient Quantum Labs is so we are basically sort of the quantum algorithms R&D arm of Quanscient, and we focus in particular on computational fluid dynamics, CFD, because that's where many sort of the intractable problems in engineering R&D lie. So if you think of solving the aerodynamics of an airplane in cruising speed with direct numerical simulation, for example, that's just intractable to any classical compute. That would take forever, and the memory just doesn't or will not ever exist for that in any classical HPC, basically. So you will need quantum computers to do that. And we believe that our quantum algorithms will be able to do that. And sort of the day-to-day work, I mean, all this requires, of course, like fundamental research in quantum computing, in computational physics, in mathematics, but also we're then, already developing sort of the first productized versions of these algorithms as well. So we're also doing sort of the development work. So it's both fundamental research and productizing this research. And we are also working already with customers in proof of concept projects.
So, talking on the fundamental side, how does quantum computing, quantum computers play along with computational fluid dynamics, for example, or physics altogether?
Right. So if you think of physics in general, I mean, physics at the fundamental level is quantum in many ways, right? So there's that. But then you might ask, like, okay, then you are solving classical physics. So how does that fit in? Well, it turns out that quantum computers can speed up also classical physics simulations, and there are sort of two major branches of algorithms sort of for that kind of stuff. So one is this sort of more linear algebra forward way of thinking, where you have your favorite discretization method, like the finite element method that we would be using, for example, on the classical side of Quanscient also. And then, what that then always ends up with is solving linear systems of equations. And there are algorithms in quantum computing that can speed up linear solvers up to exponentially. And, this will be useful eventually for sure. But this is not really what we focused on, because there are also certain drawbacks to that, and we don't see that as kind of a very near-term or even mid-term application. So rather, we've taken this sort of lattice-based algorithms that we see being much more quantum native. So these lattice-based algorithms are, well, for example, the Lattice Boltzmann method and lattice gas automata. And the Lattice Boltzmann method, the Quantum Lattice Boltzmann method in particular, is sort of our flagship method that we've been developing from the very beginning of the company. And we believe we are definitely the leading research group and leading team working on that right now. And Yeah, so these are very quantum native because you are dealing with probability density distributions of particles that you are evolving on this discrete lattice, rather than solving just linear systems of equations. You are actually circumventing the whole linear system solve altogether. So you are rather evolving these particle probability densities, and that's actually kind of already closer to the quantum nature of the world in that sense. So this is what we're actually doing. And what this allows us to do is basically exponentially large problems. So as you add qubits, quantum bits, there's problem size that you can encode grows exponentially. So with each qubit, the size of the problem is doubled, basically. And this will really allow us then to go to these massive problems like full-scale airplane aerodynamics and whatnot. But then the number of required computational operations, though, grows much more slowly than in classical methods. So that's where the sort of the algorithmic quantum advantage comes from.
Right, and how does this then these quantum algorithms, how do they sort of play together then with the classical side of things? So is there a future where one is only using these quantum power simulations, or would there still be a place for these classical simulations?
So I think there will be, and classical compute will be there, and quantum is not there to replace classical altogether. And in fact, sort of the way we see these coming together in the first place is that, well, you will, for example, training AI, you need a lot of data, and you need to train these multiphysics AI models with a lot of data, and you can do this with the classical compute quite efficiently. But then what quantum will enable there is that you can actually produce differentiated data with these exponentially large lattices and exponentially large grids, and teach something to the model that just cannot be taught at all with classical compute. But this is how these things will actually start to converge. So classical, HPC, AI, and quantum.
So you mentioned these lattice-based algorithms. Have you tested them in the real world, so to speak?
Yeah, absolutely. So yeah, we've definitely moved beyond just theory in that sense. So we've run this obviously on like quantum simulators, so a classical HPC system simulating a quantum computer, and that's how we actually do a lot of our R&D, because that's how you can really test these algorithms quite efficiently. But of course, this does not produce quantum advantage. But we've also run these already on real devices, and for example, last summer we did what we believe to be the first 3D CFD simulation on quantum computers. So we did this on IQM's 54-qubit Emerald chip. IQM is our quantum hardware partner. So we ran a 3D Quantum Lattice Boltzmann method solving a advection diffusion equation with that. And to our knowledge, this was the first in the world. And then, as I mentioned, we are also working with customers already. So we are doing this proof of concept project with some of the giants in aerospace, for example. And there we are, of course, taking real world problems, showing what can be done today with quantum computers, and what to expect as we move on to the future. So when to expect real advantages to arise.
Well, that's the $1 million question then, I suppose. So let me ask you, when do you see industry customers getting the crazy benefits and the advantages of quantum-based algorithms or simulation?
Right. So, well, first of all, they are already getting benefits through this proof of concept projects, of course. So that's one thing already now. So as I just explained, we are working with these customers to really kind of make them quantum ready already. So that's one benefit, and you really need to start to understand at this point, because well, start to understand what quantum will do for your industry, because we are really sort of nearing an inflection point when this will actually happen. And if you only start when this happens, you will be too late. But okay, so currently what we can do is these small proof of concept simulations with these quantum computers of today. So quantum computers of today, they are roughly around 100 qubits maybe, and 2 qubit fidelities of around, at best, like 99.9%. And with this we can already do these proof of concept simulations. But as the hardware is maturing quite quickly, and looking at the roadmaps of the different quantum hardware companies, we are sort of entering soon the more fault tolerant or early fault tolerant era, let's say, from this noisy intermediate scale quantum era that we're in now. And there, if we are starting to see like 99.99% 2 qubit fidelities, and again around 100 qubits or a bit more, that's when we really start to actually solve certain problems, for example in CFD, that are just intractable, for example in terms of memory to HPC. And this is when the first real advantages will arise, definitely. And at first this will be like very targeted, very maybe also like short simulations, so you're not necessarily solving again the full airplane aerodynamics at that point, but you might be solving a short period of time marching algorithm of that kind of a problem, and then teaching again the AI something that cannot be taught classically. And this is not far. So looking at the roadmaps, this is like 2-3 years that you will start to see these advantages. But then the full exponential massive advantages, this will require even better error correction algorithms and error corrected machines, fault tolerant machines. So this is like 5+ years away when you start to like really replace some of the classical HPC compute fully with quantum.
So if we go into just a bit of the specifics on what can be gained today. So let's say I was a executive or a decision maker in a automotive or aerospace company. So in very concrete terms, what is it in it for me right now, today?
Right. So basically what we do with these companies is that we together define, what sort of problems they are struggling with, what sort of problems then we could together foresee quantum computing to help them in the near future, in the mid future, in the longer term future. And then we start to validate that, for example, our Quantum Lattice Boltzmann methods right now deliver results that are delivered already, of course, by their classical algorithm, but that they are correct, and you can use these Quantum Lattice Boltzmann methods for their simulation needs. And then we kind of map the road to the future in terms of, okay, let's take the roadmaps of these quantum hardware companies, let's take the roadmaps of our algorithms, and see when do you actually expect to reach these advantages. And then also, we learn about the things that we still need to develop in our algorithms. I mean, they're not like fully ready to do everything, obviously. So we also are learning from these industry partners what we still need to develop within the algorithm so that we can actually answer their questions and answer their needs. So it's a mutual learning process in that sense. But yeah, definitely you will start to understand when your compute and when your simulations will start to make sense to transfer to quantum setting.
So then back to the technology, you already mentioned the huge mega trend of the past few years, so AI. So
Right.
Again, going into the specifics or in like more concrete terms again, how does AI and quantum computing, is there a synergy there? You also already mentioned something, but just go deeper there.
Yeah, absolutely. So yes, as I mentioned, so one thing is exactly this, that this is actually how we see the first quantum advantage arising. So it's the convergence of AI and quantum. And yeah, so basically training, for example, surrogate models, neural networks, with both classical, like massive classical compute data, and maybe a bit more scarce in the beginning, but exponentially large crits, for example, so the quantum data. And combining these to for example, for the surrogate model to learn about those really small turbulent scales that just cannot be solved classically at all. So that's the first sort of convergence of AI and quantum, I think. But then also, like already in our development and research of these algorithms, we are, for example, using AI in the sense that we are researching and using machine learning techniques to for example, replace some parts of the quantum lattice Boltzmann algorithm. So take the quantum lattice Boltzmann method. Take quantum computing. Quantum computing is inherently linear because you are dealing with unitary operations, and these are linear operations. So it's very difficult actually to compute something nonlinear. But these simulations that we want to solve, they tend to be always nonlinear, like the Navier-Stokes equation. That's a very famously or infamously nonlinear equation. So what we found out is that actually we can use some machine learning techniques to compute the nonlinear parts as a unitary operator. So we learn a unitary operator that reproduces these nonlinear parts in certain way, so that we can actually compute the full thing on a quantum computer, rather than, for example, doing some hybrid way where we compute the nonlinear parts on a classical computer and combine. So there are sort of these different ways that AI can help. And then, of course, also just, looking at all the LLMs today, of course, we are also using those in terms of programming, as everybody's doing right now. So that's also useful in quantum programming.
So, okay, what does Quanscient Quantum Labs have in store for us, the audience now? Is there something exciting we can expect in the coming months or this year?
Definitely. So, I mean, we are of course quite focused right now on some of these customer projects, but this is not stopping us to continue the research and push the frontier, so to speak. So fairly soon we will actually release a paper about a fully rewritten quantum lattice Boltzmann method, where we have actually solved many of the issues that are still present in the older papers of quantum lattice Boltzmann method that you see on arXiv and in scientific publications. And this should come out by March, I would say. And we will be making some noise about that. And we are also working, as part of this paper, we are working with our partner Haiku, and we are actually running, to our knowledge again, the first ever sort of certain type of Navier-Stokes simulations on real devices right now. And this will be hopefully published as part of the paper, but we will be also making some other noise about that. So, for example, there will be probably a webinar about that, and just, please follow us to see what happens.
Well, it sounds very exciting. Any closing words?
Okay. Well, maybe just, in terms of Quanscient as a whole. So, I mean, we aren't just building quantum software, but we really want to sort of build the future of how humanity designs the physical world. And engineers are limited by, what they can compute, and they spend billions on physical prototypes and whatnot, because simulations are just hitting the wall with classical compute. And at Quanscient, we are really tearing that wall down, and in particular at Quanscient Quantum Labs with quantum computing. And then, of course, we combine this massive cloud scaling that we have with exponential power of quantum, and soon enough, we're making it possible to simulate what seemed to be impossible. And just saying that the quantum era of engineering is coming. It's not a decade away anymore, but actually it's being built at Quanscient Quantum Labs today.
Well, thank you, Valtteri.
Thank you so much. It was a pleasure.
Thank you for listening to this episode of The State of Simulation. To stay updated with the latest episodes, webinars, blogs, white papers, and more, join our community of more than 7,000 engineers and engineer-minded people on our LinkedIn page, Quanscient. Thank you again, and see you in the next one.